Hey, welcome back. So, CPU versus GPU. You've definitely heard both of these terms, probably 100 times. CPU is the processor. GPU is the graphics card, right? Simple. Except here's the thing. Right now, in 2026, the most powerful AI systems on the planet are being run on GPUs, not CPUs. Nvidia, a graphics card company, is suddenly worth more than most countries' entire economies. And people are asking why. Why is a chip designed to push pixels in video games now the engine behind ChatGPT, self-driving cars, and drug discovery? That question has a genuinely fascinating answer. Let's get into it. Before we compare them, we need to understand what they were each built to do. The CPU, Central Processing Unit, is the brain of your computer. It has been since the very beginning of personal computing. Intel released their first commercial CPU back in 1971. Everything your computer does, opening apps, running your operating system, loading a web page, calculating your spreadsheet, that's the CPU. It is a brilliant generalist. It can handle almost any task you throw at it, and it handles them one after another with incredible speed and precision. The GPU, Graphics Processing Unit, came much later, and for a very specific reason. As video games and 3D graphics exploded in popularity through the 1990s, developers needed to render millions of tiny colored squares, pixels, onto a screen, 60 times per second. The CPU simply couldn't keep up with that workload on top of everything else it was doing. So engineers pulled that specific job out and gave it its own dedicated chip. Nvidia released one of the first modern GPUs in 1999, the GeForce 256, and the gaming world was never the same. Here is the core idea, and this is the part that makes everything click. A CPU is like a master chef, highly skilled, trained for every situation, capable of making a 5-course meal entirely alone. Give it any task, complex, unusual, unpredictable, and it figures it out. A GPU is like a factory kitchen with thousands of line cooks. None of them individually is as skilled as the master chef. But if you need to slice 10,000 onions at once, the factory wins, and it isn't even close. Different tools. Completely different design philosophies. Let's put some real numbers to this. A modern high-end CPU, something like an Intel Core i9 or AMD Ryzen 9, has somewhere between 16 and 32 cores. Each core is an incredibly powerful, independent processing unit. A modern high-end GPU, something like an Nvidia RTX 4090, has over 16,000 shader cores. They are smaller and simpler than CPU cores, but there are thousands upon thousands of them, all running at the same time. That is what parallel processing means. Not doing one thing faster, doing thousands of things simultaneously. And this is exactly why gaming GPUs are so powerful at rendering graphics. When your GPU is drawing a frame in a video game, it is calculating the color, lighting, and shadow for millions of pixels all at once, in parallel. If you tried to do that pixel by pixel on a CPU, even a fast one, your game would run at about 3 frames per second. You'd think your computer was broken. The GPU doesn't compute harder, it computes wider. Now, here is where things get genuinely interesting, and where the AI story begins. Training an AI model at its mathematical core is essentially this. Take enormous tables of numbers, called matrices, and multiply them together, millions of times, over and over. And here is the thing about matrix multiplication. Every single calculation in that operation is independent of the others. They do not need to happen in sequence. They can all happen at the exact same time, which means they map perfectly onto a GPU. It is almost as if the GPU was designed for this, except it wasn't. It was designed for video games. The maths just happened to be the same. Nvidia figured this out in the late 2000s. 2 researchers at Stanford, training an early neural network, tried running their model on a GPU instead of a CPU, and the training was 70 times faster. 70 times. That result spread through the AI research community like wildfire. Nvidia saw where this was going, and in 2006 released CUDA, a platform that let developers use GPU power for non-graphics tasks. That decision quietly changed the trajectory of the entire technology industry. So, where do you actually find CPUs today? Everywhere that involves complex, varied, unpredictable work. Your laptop, your desktop, your phone's main processor, the servers handling your bank transactions, the logic running inside your smart fridge. Basically, anywhere a computer needs to think flexibly and respond to whatever comes next, a CPU is in charge. Intel and AMD dominate the traditional CPU market, though ARM-based chips from Apple and Qualcomm are giving them serious competition. But that's a whole other video. GPUs, meanwhile, have quietly taken over the most computationally intensive work on the planet. Video games, obviously, but also video editing and 3D rendering, where professionals live or die by GPU performance. Cryptocurrency mining, which drove GPU prices absolutely wild for a few years. And now, AI training and inference, which has become the dominant workload. Nvidia's data center GPU revenue has grown from almost nothing a few years ago to tens of billions of dollars annually. The H100 chip, Nvidia's flagship AI GPU, sells for around $30,000 per unit. Companies are buying them by the thousands. Here is one that surprises people. Your CPU and GPU are not enemies. They are partners. In almost every computing task, they divide the work between them. Your CPU handles the game's logic, what the enemy AI decides to do, where your character is in the world, what sounds play. Your GPU handles what that looks like on screen. In AI, your CPU manages the data pipeline, shuffles data in and out of memory, and coordinates everything, while the GPU does the heavy number crunching. Neither one could do the job alone. The CPU is the manager. The GPU is the workforce. Now, CPUs have not sat still watching this happen. Modern CPUs have added small sets of dedicated cores specifically designed for AI tasks, what Intel calls NPUs, or neural processing units, built right onto the chip. Apple's M-series chips have had dedicated neural engines since the M1 in 2020. Qualcomm's Snapdragon chips have them too. The idea is to handle lightweight, everyday AI tasks, things like autocomplete real-time translation, background blur on your camera, locally on your device, without needing a data center full of GPUs. The lines are genuinely blurring. But let's not get ahead of ourselves. For serious AI workloads, training large language models, generating video, running simulations, GPU remains completely dominant and will be for the foreseeable future. Nvidia has such a commanding lead in both hardware and software tooling that competitors are years behind. AMD is making real progress with their Instinct GPU line. Google has their own custom AI chips called TPUs. But Nvidia's CUDA ecosystem, built over nearly 2 decades, is a moat that is very hard to cross. All right, let's put it all on the table. Design purpose. CPU built for general purpose, flexible computing. GPU built for parallel, repetitive tasks at massive scale. Core count. CPU has tens of powerful cores. GPU has thousands of smaller ones. Speed. CPU wins at complex sequential tasks. GPU wins at doing thousands of simple tasks simultaneously. Primary use. CPU handles your operating system, apps, logic. GPU handles graphics, AI, video. AI performance, CPU capable but limited. GPU is the undisputed champion. Key players, Intel and AMD lead CPUs. Nvidia dominates GPUs, with AMD and Google competing. That is your scorecard. And there you have it. CPU versus GPU, fully unpacked. The big takeaway is this: the CPU is irreplaceable for the unpredictable, complex thinking that running a computer requires. The GPU is irreplaceable for the raw, parallel number crunching that modern AI demands. What makes this moment so remarkable is that a chip originally built so teenagers could play better video games is now the foundation of one of the most significant technological shifts in human history. Nobody planned that. It just turned out the maths was the same. And if that is not a fascinating accident, I don't know what is. If you enjoyed this, smash that like button, subscribe, and I'll see you in the next one.